If you know Mitchell, he's got so many letters behind his name. You know, he's a medical doctor. He's got a doctor of engineering, and I think he should probably have a Juris Doctorate after the battle he's been in with the patent office, and I think has won something. So, in any event, we're fortunate to have Mitchell. And last night he said he had 250 slides that he had to go through and cut it in half. And I said, I've got a hook. So, Mitchell, my good friend.
Thank you. I'm going to try and give a few hints on how you can get more active cells in your cold fusion lattice systems. And to do that, I'm going to show how this works in both aqueous systems and in the nanostructured dry preloaded systems. Let's see. There's been a lot of talk here that there have not been recipes given by people in the field. If you want to go back, there's a terrific recipe in the proceedings of ICCF-10. We told how you could make a high impedance fusor type cathode, which gives reproducible excess heat with heavy water. Today's talk is on the fact that when we electrically drive systems, we often have two modes that they work. One where we're producing excess heat and one where it's inactive. In fact, so this is the inactive, this is where we get excess heat, and this is a summary of what we'll be talking about today. So the first question is, flight is a good analogy of getting excess heat from a cold fusion system. Langley's crash is here in October 1903. Followed by the Wright brothers with success. Why is one working? Why is one not? Well, it turns out that in aerodynamics, if you achieve active flight, you have a conformance flow over the wing, but if you lose it, you get into a stall. And a spin here is just an aggravated stall with a rotation around the center of mass. So first of all, I want you to think of cold fusion as being very much like flight. We can fly it, or we can crash and get excess heat. And I'm going to show you example after example of a theory that explains this, and multiple examples of actual experiments with aqueous fusor-type components and with the dry preloaded NANR-type components. And by the way, here's another interesting thing. When you look at the aerodynamics of flight, what we see is there's optimal operating points. And if you're above here, you get into a stall. We're going to see the same curve occurs in cold fusion. And if you want success, there are two states, and we will distinguish these modes, the active mode and the inactive mode. And the implication is if you want success, you must drive your system in the active mode and avoid falling into the inactive mode. Okay, now in order to see these two modes, we're going to see it 4 different ways or 5 different ways. We're going to show it by calorimetry. We're going to show it by changes in electrical conductivity. We're going to show it by the development or loss of the anti-Stokes signature. And we'll talk about each of these. And then I'll show that the optimal operating point manifold, that curve I show, where if you look at the excess heat as a function of input power, it goes up and up, hits a peak, and comes down. And if you know your system and drive it at the peak, you'll get the two things happen. One, you get the maximum performance of your system, and two, you have a way of identifying which materials work, because now you can have standardization. If you're able to standardize your treatment of these materials, then you can tell which ones work. It's hard for me to read it. Okay, so we're up to 2. First thing I want to do is talk about the very successful theory that was developed, the quasi-one-dimensional model of isotope loading, and from it has come all kinds of discoveries that have panned out. This was the paper that I published in Fusion Technology that describes this theory, and from it has come the high-impedance aqueous systems, a different type of co-deposition than Spey-Wars is doing, but still gives excess heat. The fusor-type aqueous components, the optimal operating manifolds, and our control of heat after death, which we call tardive excess thermal power. To understand the quasi one-dimensional model, we start off with a simple equation. The flow of deuterons is equal to an electrical term and a flow down a diffusion gradient, if this isn't familiar to you. And if we take this equation and we divide by concentration, we get a first order, we get the loading rate into the palladium is equal to the electric field times the electrophoretic mobility minus these terms, what goes up in the gas, and this tiny term, which is close to zero, which is how much we're making helium-4, or whatever other products we're making. So here's the equation when we solve it out, and if we put in the Einstein relation, we get this. And this is the take-home point. If you see bubbling in an aqueous system, you're setting up a pathway of failure. The trick with this is to get the maximum loading and not get the gas phase. And we'll see that in a second. And what's panned out of this successfully is a whole series of papers on the aqueous fusor systems, and then we developed all these other things. All of that came out of the model. So let's talk about the high impedance systems. We tried all kinds of ways of hitting break-even, and break-even is just, I use DC. We don't use pulses, we just put on a voltage at steady state, and then we measure the input power easily, V times I. We measure the output heat by simple calorimetry. And we tried all kinds of things, nothing worked. And finally, we did this coil, and we've suddenly had an improvement. And what we found was, Fleischmann and Pons, if you use 2 wires, you don't get flow through the metal. And if you use the coil, you get flow through the metal. And we think that's one of the keys that's going on here. And to prove it, here's the results. This is this is an ordinary water system that is a gold anode and a nickel cathode, and we're driving it with ordinary water. And here we're measuring the noise. Here's an ohma control, a nice match of the input and the output. And here we're putting on the input here, and we're getting the output here. This is energy. The energy curves go to the right, the power curves go to the left. So we can see we get excess heat, and the reason we're doing it this way is we're working out the optimal operating point. Here is with a palladium heavy water system with a platinum electrode, and here is the ohma control. And here we're putting input into the aqueous system. Here's the output, and again, we get higher output here. And this is what we showed at the open demonstration at ICCF-10, where it ran for 3 days, and we got 2.5 times out what we put in, and that's measuring the input as V times I. And here it's a longer run. We did this when Popular Mechanics came by to see it. And so this is a multi-day run. Ohma control, ohma control, ohma control, and we clearly are getting excess heat each time. Here's another one with ordinary water and nickel. This is what we set up at the MIT ICCF-10. We run the cells in electrical series. We use DC voltage. It's a you can't get a simpler system to show excess heat. And so we ran over 3 days. We showed the optimal operating point. That was the size of our old fusor. This is the size of the new ones. And if you go to the poster, you'll see some of the results. This year, we're showing the results from about 10 years ago, where we saw a loss of deuterium, and the high power drive of the system we'll show later. Is there any water around? Is there some here? Yeah, that'd be great. The other thing we got was control of heat after death. And here you see that here's our noise measurement. This is power read off to the left, energy read off to the right. Thank you. Thank you so much. And what you see here is we used heat after death to do work. And this is our first measurement where we're taking the heat that's coming after we drive and using it to heat up an ohmic load at a second location. In controlling heat after death, we can actually, by pulsing and then controlling later, increase the gain of the system even beyond what we measure. So here what we're getting is an additional gain of a factor of 400%, what we get over a continuous measurement. This is a massive way of getting more excess heat out. And what we did with that was we used paired Stirling engines. And this was enough to convince DTRA to take the first grant, to take the first proposals in the government and award money for cold fusion. Because here we have an electrical current going through these two cells that you can't see in here, and the heat comes up to these Stirling engines. So we drive with the same power because we match the impedances, and one of the wheels is flying around over the cold fusion cell, and the other one isn't spinning at all. And we ran this for months and months with all kinds of devices. And here you can see the output. And the other thing we get out of this is we're able to measure the parameters inside the palladium in heat after death. Okay, the other thing I want to show you that came out of the quasi-one-dimensional model is this optimal operating point manifold. And it's really important because when I consider cold fusion systems, we look as a function of input power. And maybe that's very related to what was discussed yesterday, that we're not dealing with a Coulomb barrier, but a momentum barrier. And what we find is for heat production with palladium, it matches the helium production. I got this data from Mel Miles, and I asked him to look in his notebook for the voltages. He had only published the currents. And when I plotted them out, to my astonishment, everything came out perfect. So I have no doubt that what he measured was accurate. Here's an optimal operating point manifold for the fusor. Here are the ohmic controls. They're all below break even. And we're getting excess power up to 4 watts here. Now, I believe that when we look at this, we're getting insufficient loading on this side. We're getting wasteful electrolysis on the right, and this is where you want to drive the system if you want to standardize. Here's another one. We worked for years getting these optimal operating point manifolds, and by driving it for months and months, we got a beautiful curve here. And you want to know something amazing? When I look at our curve, and last week when I started looking at the stall curves for airplanes, they match. And I think that's trying to tell us something, though I don't know what. Okay, let's go to the next thing. Peter Hagelstein and I showed at ICCF-21 that there were 2 states in these preloaded nanomaterials. These are some of the NANR-type components that we made. These are the Series 7s that we showed at MIT, and then we have some newer ones. And again, we do simple calorimetry. We take the ohmic control, we put it next to the NANR-type component, we put it in a calorimeter, and we use direct current. So it couldn't be easier, and therefore we can measure the ratio of the heat coming out of the two. And what we find is these NANR-type components actually have quite a bit of power on a Rangone plot. They're way out here, out near plutonium. And we used the NANR-type component with the drivers in the MIT courses in 2012 to teach cold fusion. And here's one of the outputs. Here we're looking at the power in watts, the input. This is the energy in joules. The dotted curves go to the right. We use an ohmic control. Here is the input to the ohmic control. The output of the heat's a match. Here's the input to the NANR-type component, and we get a massive output. At MIT, the NANR-type component that we showed had a gain of 12 times input, and we've gone a bit higher, and we'll talk about that some other time. Okay, let's look at this now to go between 2 states. So here we do calibration pulses. I want to make sure that all the measurements in the computer are accurate. So we take out our instruments and measure it, and we do a control pulse. That's what you're seeing here. Here's the ohmic control. We get a nice match, another pulse. And here's the NANR-type component. Here's the output. And what's interesting is what happens with nanomaterial components is above a certain voltage, they'll avalanche. You won't get excess heat. There's two states. So let's look here. The ratio of the change in temperature to the power in is what we're looking at here. That's the amount of heat coming out to first order. So here is our input. Here's the heat out of the ohmic control, much less input to the nanotype component, and massive heat comes out. And as we raise the voltage, because remember, we're doing optimal operating point operation. We're starting at low voltage, we're going higher and higher, because we want to characterize the material. All of a sudden, we get an avalanche, and look at this. It matches the ohmic control. That was our first indication in one experiment of two states. When you do an experiment and you're not getting a result, you may be driving it in a mode where it's inactive. And this is confirmed. We use heat flow sensors. We do a lot of multiple ways of checking beyond calorimetry. So even with the heat flow sensor, here's the ohmic control, here's the amount of heat flow with the ohmic control, here's the amount of heat flow with the nanotype component, had less input power going into it, and all of a sudden, we go to the avalanche and we're not making the heat. That was our first indication. And here, if we look at the incremental power gain, I use that instead of COP, but they're almost interchangeable. We see we start off with a COP or incremental power gain of 6. That's 6 times the electrical input, and it drops down, and once we hit the avalanche, bang, it matches the ohmic control. And that was from the picture I showed at the abstract. So the take-home point of this, if you work with nanomaterials, you must be below the voltage where the avalanche occurs, because if you exceed it, you'll never get excess heat. Okay, now here we confirm the two states by using Raman spectroscopy, coherent Raman spectroscopy. Raman spectroscopy is actually very weak, and he mentioned that when he won the Nobel Prize. And when we got the results, Peter Hagelstein said to me, these peaks are very big. And if you look at it, by using coherent radiation rather than non-coherent radiation, the gain of the Stokes peaks goes up by 10 to the 6. And that's why you're going to see what we're doing is we're using 2 lasers to irradiate the dry preloaded nanotype component. We'll look at the output, put it through a grating, look at a detector, and what we end up is seeing this. So here is the LANR off, okay? And when it's on, there's 2 states, and we can distinguish them by optical spectroscopy using coherent Stokes, what we call Seymour spectroscopy. So here is during the avalanche, there's no excess heat. And here, we're getting excess heat. When we get large anti-Stokes, that means the light hits the material, the phonon energy is added into that photon, and it comes out at a higher energy. So we hit with green, this is towards the blue. Normally, you only see towards the red. And what we see here is evidence of excess heat before we see it in the calorimetry. By using this technique, we can actually determine immediately if we have an active system. And the other thing that's nice, if we plot it out on a log scale, we can see the optical phonons down here. These are acoustic phonons. Okay. Now, the 2-state system was confirmed by Peter and Florian at MIT. I gave them a series of nanotype components. And so, for example, Florian is a meticulous investigator. And here, he's driving the ohmic control. We are looking at the electrical resistance. Remember, there's 3 ways of determining these 2 states. You can do it electrically, you can do it by calorimetry, you can do it optically. And here is the ohmic control, and here we're getting an active system, and suddenly it collapses to ohmic levels. And we see this over and over. Here, for example, with which component? This is a different one. This is series 8-2. Here's his ohmic control. Here he's putting in power into the nanotype component. And we can see there's clearly 2 states. When we're getting what we want, and here we're looking at the output power in a very tiny amount, but Here, when we get active system, it is at a different level from when it drops back to the OMA control. And here's an even better one. Here, we're getting activity. Here, we're getting a complete match to the OMA control. I better go faster. Again, desired behavior, and when we fail, we match with the OMA control. I'm going to skip this, otherwise I'll run out of time. It turns out this is also true for aqueous systems and the MOAC, the mother of all cathodes is what MOAC means. It has a half a mile of wire, and the picture's over in the posters. And here you can see the two states. Here's the control. We always do a control before we run the cell. And so here's our input power, and here's our heat out. And look at this tiny amount we're putting into the cold fusion cell, and we get more heat out. But if I drive it higher, all of a sudden we get the electrolysis, and look what happens. Hydrogen comes out, and the excess heat falls. So now we're seeing the two states in both the nanomaterials and in the aqueous systems. And this is in your abstract. We can see that, again, this is a different run. And here is the OMA control. Here is the heat out. And here, you can almost not even see it, the input to the MOAC, and a massive amount of heat production until we make hydrogen evolution by driving it up higher. So, two states have now been confirmed by the spectroscopy, by the transconduction impedance, and by the excess heat itself. This is the anti-Stokes appearing on the MOAC. When we drove it in excess heat mode, we can see that there's an anti-Stokes. And when we're not getting the excess heat, there's no anti-Stokes. I really recommend all of you who work in this field start looking at anti-Stokes. It's a terrific way to tell if you have an active system. In my last 3 minutes, I'm going to wreck this fantasy. And that is, it's more complicated. There's 3 states. We can destroy our systems. And I don't know how much time I'm going to have, but I will try to do it just for nickel if I can. If you go back to our paper at ICCF-21, we showed that if you add deuterium to ordinary water and nickel, that you can get more excess heat out. But you wreck the nickel. So here, for example, I'm adding 4%, 7%, 14% heavy water. Here's our control, the OMA control. Here's ordinary water. Here's with the added D2O. And here's with the actual calorimetry, the noise measurements. The nickel changes. I wish things were simple. Unlike palladium, nickel will change if you use too much deuterium. It'll change color. It'll change 4-point electrical impedance, and it'll never give excess heat. So here are the OMA controls. Here is the nickel before it changed color, and here is when it's damaged and it never worked again. See, damaged, OMA control, fusor. So to make, I could show you, we have 1 minute left. It turns out the same thing is true with aqueous systems. I'm not going to have enough time. But basically the point is, take out there's 2 states. There's an active state and an inactive state, and you really want to avoid going to irreversibly inactive. That's it.
We've got a little bit of time for a question, but please make them short.
Thank you for a great presentation. I have a question about the possible connection to the role of the ion diffusion that was discussed yesterday. So yesterday, the colleagues from university in Japan discussed the suggestion that the diffusion of ions across the interface plays a role. Do you think that that model could apply here so that when you have this anti-Stokes phenomenon, then what we see is that electric voltage is driving protons into the lattice, and that's how you see the phonons. And when you see electrolysis, then the evolution of hydrogen happens before protons enter into the metal. Do you think that's a feasible model, or you have other ideas about?
I have to think about it. I haven't thought about that, what the origin is. I just think about it systematically that when we have excess heat, there is phonon activity, and there's enough around that if we have an incident photon, we can actually drive it back up. I hadn't thought about the structure. I'll have to do that.
Thank you.
Thank you.
Okay,
I have a question and a comment.
The answer gets long. I'm going to ask you to take it to the
Back.
the back or the poster session. So please. Yeah.
So my question is about the different states that you refer to, Mitchell. Do you have any thoughts on what the mechanism, the underlying mechanism could be for these different states? And my comment is referring to the data that you presented and I was involved in. I just wanted to mention that we're still very much in ongoing discussions on the interpretation of that data.
I believe that when we lose activity, we're setting up alternate pathways, and that they're easier to go to, and even if they're the same, we lose half of it. So I think what happens is our goal is to try and set up as much as we can a single pathway to excess heat.
Just a quick question. What in the electrolytic systems, when you start producing bubbles, can you come back?
Will what come back?
The excess power.
Yes, yes, if you lower the voltage, yes, with
Yeah,
palladium.